One example for neural networks is image recognition. It's a bunch of images of handwritten digits from 0 to 9. And the task there is to figure out from the image what number is represented.
How do you even get the machine to see that handwritten thing? Like, because the machine only reads zeros and ones.
Yeah.
First, you have to tell the machine that within the zeros and ones, there is like a white paper in which there is a squiggly line in this pattern. Like that itself seems so challenging.
So that's actually a great question. I think that's a really good segue. You can't do that with this, but you can do it with neural networks, and I can explain to you exactly how we'll. Hey, welcome to the Art and Science of AI. You're listening to Season 1, which we recorded in May 2023 as a continuous 3-hour-long conversation. Season 2 is now live, so if you're enjoying this discussion, please subscribe for new episodes every week.
Right. Okay, so let's go beyond classical.
Yeah, that's the next thing here. So the concept of a neural network, it's inspired by the human brain, where the brain consists of a bunch of neurons that are either activated or not. And each neuron, so we have a bunch of neurons that are interconnected.
Yeah.
And neurons activate in regular patterns. Like when you see an image or when you have like a happy moment, say when you see your daughter, right, and you're happy, you have some emotion, that activates a certain set of neurons, and there's a pattern to that, and that activation then has a certain output, which is like you feeling happy. So basically the idea is, can we construct an artificial system that's somewhat similar to that, with a bunch of interconnected neurons, and try to figure out patterns of activation that map to certain types of input? It's very abstract, but I can actually go into an example.
Help me understand it this way. Like, I really like the way the reason we went into machine learning is because you explained to me the challenge with the classical approach to programming. It's like when you do rule-based programming, after a while, you hit a wall, which is why you needed to find new and novel approaches. And the new and novel approach was machine learning. Now, like, is it similar to that? Like, did we hit a wall with classical ML
The wall you hit is, firstly, you need to handcraft these features. Like, you need to know what are the exact features I need, like number of rooms or square footage or whatever. That's one. But I would say the main wall you hit is it can't work with unstructured data. Like so there's a distinction between structured and unstructured data.
Right.
Structured data is like this. It's the kind of thing you would put inside a SQL database.
Right, like a spreadsheet or something.
Or a spreadsheet. You have rows and columns, and this is very structured data.
Named rows and columns.
Yeah, exactly. What is unstructured data? Unstructured data is like a paragraph of text. Unstructured data is an image.
Right.
That's completely unstructured.
Right.
So the classical ML is not good at dealing with unstructured data. I can't feed it an image. I don't even know, like, what am I doing with this image? Like so actually the one example I want to talk through for neural networks is image recognition.
Right.
So there's this very famous task. It's called handwriting digit recognition. There's a database called MNIST. I don't even know what it stands for, but basically it's a bunch of images of handwritten digits from 0 to 9. People handwrite, like you write 7, 8, whatever. And the task there is to figure out from the image what number is represented.
Okay.
So think about that task. I'm just giving you, it's like,
dude, I don't even know where to start.
How would you even, what is the feature here? How do you extract a feature? So this stuff doesn't work in that context.
I've thought about this before, and I was like, I don't even know how to think about this. Like, first of all, how do you even get the machine to see that handwritten thing? Like, I'm like lost there already.
Yeah.
Like, what is it? See, let me explain to you what I mean. When let's say my baby girl, Isha, she's 6 months old, right?
Yeah.
I'm going to show her an 8.
Yeah.
She does not know what an 8 is. For her, it's just an abstract squiggly line.
Mm-hmm.
But at least she can see that in a white piece of paper, there is a contrast, and she can determine that there's a squiggly line in the shape of an 8. I'm saying, how do you even show the machine?
Yeah.
Because the machine only reads zeros and ones.
Yeah.
First, you have to tell the machine that within the zeros and ones, there is like a white paper in which there is a squiggly line in this pattern. Like that itself seems so challenging.
So that's actually a great question. I think that's a really good segue. You can't do that with this, but you can do it with neural networks, and I can explain to you exactly how we'll do it.
That'd be amazing, because I always... Do you understand my question? Like
I have the answer to your exact question next. Okay, so this is abstractly what a neural network is. And this will become more clear with this example of the handwriting recognition that we're going to talk about. But there's an input layer, and then these are the things that are called neurons. Each neuron is like a neuron in your brain. We don't actually know if this is how the brain works at all. It's just a theory, a hypothesis. But what happens is each neuron either gets activated or not. And then that signal passes through to the next layer. And finally, there's an output layer that gives you the answer you want. This probably doesn't make sense now. Let's go through the example, and then we can see how it makes sense.
Yeah.
So the input layer, it receives the inputs. The output layer is like the final layer that creates like the response, and the hidden layer is what's doing the manipulations in between. Like it's doing the...
What example are we following here? Is that
handwriting
an input
recognition
of a handwritten digit from anywhere between 0 and 9?
0 to 9, yeah.
The goal of this model is to predict
which digit that is. Yeah, exactly. So in that case, actually, let's think about what is the input layer to that, okay? What am I going to input from the image? Like, do you have any ideas?
No, I mean, that's my question. Like,
okay.
Like, how do you break down an image to a machine?
Okay.
Am I wrong in thinking that a machine can only see zeros and ones?
Sure.
Like a machine literally can only see a high voltage or a low voltage, which is then represented in 0 and 1.
So let's take a simplifying example. Let's say these images are all black and white, okay? Or let's say they're grayscale. That's like simpler than
let's do black and white. Yeah.
So grayscale. And in this particular data set in MNIST, they're 28 pixels by 28 pixels.
Okay.
And 28 multiplied by 28 is 784. So there's 784 pixels.
Okay.
Each pixel is an input. And the value of each pixel is between 0 to 1. 1 is if it's totally black. 0 is if it's totally white. And in between is how gray it is. That's how grayscale images are encoded.
Oh, I see. Okay. So if it's an 8... you'll take like a square pixelized image.
28 by 28.
Right.
Yeah. You sequence it into 784
and
pixels.
All the places where it's actually 8, let's say it'll be 1. And all the places where it's just white paper, it'll be 0.
Yeah. Or that's, if it's black and white, that's what it is. If it's grayscale, it's more sophisticated. You have an entire scale between 0 and 1. How 1 is most black, 0 is most white.
For simplicity's sake, let's take black and white. It's like a squiggly line, but it's like a...
Yeah, then it's zeros and ones, exactly.
Pen to paper is 1. Yeah. Only paper is 0. Let's simplify it.
Exactly.
Okay.
Yeah.
Okay.
Yeah, that's a simplified example. Realistically, it would be grayscale because there are some places where it's like maybe...
Yeah.
And it's easy to generalize this to a color image, like because color, you break it down into RGB values and you say 784 pixels times 3. For each pixel, I'll give you an R, G, and B value.
Right.
That's how you would convert it. Yeah.
Oh, that's another cool computer thing that you can break down. I mean, well, computers adopted it from the primary colors, but I see what you mean.
Yeah, you can compose.
You can create any color from RGB, basically.
Exactly.
Yeah.
So in this case, let's just simplify it and say it's only grayscale, or you can think about it's only black and white. 784 pixels, that's the input layer. What you want out of the output layer is finally a number, right? 1 to 9. Right. But realistically, what happens is your output layer has 9 neurons. Each of them are numbered 0 to 9. And the output is a prediction of between probability of how likely is it that this image is a 8. So suppose you feed it a 7.
Got it.
And
if it's my handwriting is...
because ideally, sometimes there will be... it won't always be 100% certain. So
like a 4 may look like a 9, depending on how you do it.
Yeah.
Got it. Okay.
So the goal is that when you feed in a 7, all the pixels go in.
Right.
And the layer corresponding to the 7 is the one that lights up the most.
Right.
Okay. So let me show you an example of what this looks
that's
like.
Cool.
This neural network. So the input layer is, as I said, 784. input neurons. Okay, that's how big the input layer is, because we said 28 by 28, and that's each pixel. And yeah, you can think of these greens as the activations. The blank ones are not activated. In this case, actually, there's shades of green because it's grayscale. And then this output layer for this 7, it's activating this 7, which means that it correctly recognized that it is 7. And then there are these two things in between called hidden layers. That's where the manipulation is happening. That's where the weights and parameters are coming in.
That's the magic. That's the secret sauce.
Yeah, exactly. That's where the magic is happening. So it's just like the case earlier we talked about with a linear regression. First, you start with some random way of activating things, and then you evaluate the loss, and then you look at how do I optimize this. So actually, let's go back to this list here and think about what all these things here correspond to. Maybe you can start with features. That's an easy one to start with. In this case, features there are 784 features, each pixel value. That's it.
Right.
Where in the home prices case, remember we had square
one
footage,
feature.
or yeah, we had only one feature.
Right.
In this case, we have 784 features that we're putting in. Model architecture, it's a little complex, but it's what I showed you in that diagram.
Instead of linear regression, it's neural networks.
It's a neural network.
Okay.
Yeah. Parameters. Okay, before we talk about parameters, let's talk about the objective function. The objective function, again, as always, is to minimize the loss. So just as, remember, in the regression case, we talked about...
You start with one random line and then you move it towards...
Yeah, but what is the objective function? We're measuring what is the distance between that line and the actual
data
houses.
plot.
Yeah. So in this case, what we do is, once we create a model, we put all our data through it, and we measure the distance between the predictions and the actual values. That's always what an objective function is. You want to minimize the distance between your predicted values and the actual values.
Right.
So the predicted values, for the data set you fed it, it may be like 0, 1, 2, whatever. Actual values may be something completely different. And you come up with a way to measure the distance between those two. That's the objective function that you're trying to minimize.
Right.
And then
so I see what you mean. So you're saying that in this case, in this model, you'll start with, like, let's say 100 examples.
Yeah.
Of like
that's
papers.
The training data.
Yeah, the training data would be a bunch of places, papers, 28 by 28 pixels, where you've written a bunch of numbers. And obviously you know what the number is, so you're training the data. So you'll start with your 784 input data. You obviously know what the answer is. So probability will be 1, right? But what's happening in like what actually happens during the training?
Let's talk about that. So let's talk about what's happening in these hidden layers. So there's a thing called an activation function here, which is there are lines connecting every node to every other node in the next layer. Okay. In this architecture, we're just assuming I have 2 hidden layers. Each of them has 16 neurons in this example. It's just arbitrary. We can't really get into like why there are 16.
Right.
Arbitrarily, we assume there are 2 layers and 16. This is describing what's happening at the first layer. For each connection between a neuron in this layer and a neuron in this layer, it has a weight.
Right.
Okay, so these all have activations that are A1 through AN, and then they all have weights. So suppose here, I want to compute the activation here. Why is this green? Why is that lighting up as opposed to not lighting up? So what I'm doing is I compute the activation function of that neuron. This neuron is connected to 784 input neurons. And through this function here, it's just a random set of weights and biases. I determine whether this should be activated or not. And it's going to give me like a 1 or a 0. Or it could be anything between a 0 and a 1. So it's going to output an activation. And then the same thing is happening at the next layer again, but much smaller because I have only 16 now. And the same thing is happening at the final layer. So there are only 16 things here.
So does it progressively reduce the hidden layer? So like the first one's 16, the next one's what?
In this case, they're both 16, but it progressively does reduce.
Yeah, it reduces. Okay.
Yeah.
And then eventually it'll come to the
idea of what we think is going on here, we really don't know, is that each layer is developing some abstraction over the first layer is literally looking at individual pixels. The next layer, we think, is learning some patterns behind those pixels. Like, oh, does it have a straight line? Does it have a loop? Something like this. And then each subsequent layer is a higher level of abstraction until you get to the final layer that tells you what number it actually is.
Right. Okay.
That's what's happening in this. So now I just want us to think about how many parameters there are here. So each neuron is connected to each other neuron in the next layer. 784 connected to 16 neurons here. And each one also has a bias. Bias just means, like in this case, like this parameter that's not a coefficient of any feature, we just call that the bias.
Right. Like 100 in this case is the bias.
100 in this case. So in this case, like each neuron has its own bias and n weights.
So are you saying that so the hidden layers right now, for simplicity's sake, there are only 2 hidden layers, but it could be any number of hidden layers? You're saying the first one, when you start training the data, you just start with something random?
Yes. Okay, first let's think about what all the parameters are. Let's go here and see. There are going to be 784 times 16. This is the number of parameters for these connections.
Right.
16 times 16 is the number of parameters for these connections. And 16 times 10 is the number of parameters there. And there are this many biases because each neuron has its own bias. So there are 13,000 parameters in... Sorry, I'm getting sun in my eye. There are 13,000 parameters in this model. So remember we talked about with linear regression, all that's happening is first you initialize a random set of parameters and then you move towards the right direction to get the right parameters that are minimizing your loss function. Loss function is just the inverse of objective function here, that are optimizing your objective function. And the way this happens, it's a combination of something called backpropagation and gradient descent, which we talked about earlier. So when there's an error here, like, suppose it recognized the ones as zeros instead, based on the error that we find from the objective function's value, it knows like how to propagate backwards and adjust the weights to get to the right direction to optimize the objective function. So that's all that's happening. It's just like linear regression on like a hyperdimensional scale. You're just tweaking the parameters like in an intelligent, non-random way. You could theoretically, like, remember originally you said like we can draw 1,000 lines for regression and find which is the best. Theoretically, you could do this. If you had infinite computational power, you could just generate like infinite combinations of these 13,000 parameters and just say select the best one. That itself would be like a way to do it. But since we don't have infinite computational power, we want to optimize. We want to test only the relevant combination. So every time we know which direction to go in based on this gradient descent thing, and it moves in that direction and only tweaks the parameters in one way until it gets to the optimal set of parameters that can most accurately predict the digits.
So what I understand from this is the breakthrough over here with neural nets. So like I'm gonna like summarize our story. Our story is classical programming hits a wall. Then you have classical ML, hits a wall. Then the breakthrough is neural nets. What's the breakthrough with classical ML? The breakthrough is instead of you programming the rules, the algorithm figures out the rules. What is the breakthrough here? Is it the hidden layers and this back propagation thing?
The breakthrough is that you don't need to figure out how to structure the data. Like, remember in the classical ML, I have to structure the data and say, this is the feature. Like, the feature is like the number of rooms or the number of houses. Here, you don't have to structure the data. I just give it 784 pixels.
I see what you mean. Yeah, you're just giving it raw pixels.
Exactly. Or in the case of language models, which we'll talk about next, it's raw text that you will give it. So I don't have to structure the data at all. And I don't have to structure the features. Like, because again, in classical ML, typically, there's a lot of handcrafting of features that you have to do. In a regression model, sometimes you will find that like linear regression may just be the wrong example. Linear regression means there's a straight line relationship between the two variables you're trying to plot, but maybe there isn't. Maybe it's a polynomial like equation. So it takes a lot of time to customize and find the right one that fits your data. In this case, you have to do none of that. It's just an abstract structure that can apply to like many different types of data sets.
It also sounds to me like every next evolution, we're making it simpler in some sense. Obviously, we're taking advantage of the massive computational power, but...
Can we get another beer?
So, like, let me explain how I mean it. So, in the first case, we had to do the one-on-one, like, we had to create the rules, right?
Yeah.
Now, in classical ML, you don't have to create the rule.
Can we get the hazy?
in the classical ML, you don't have to get the rules. So like from the programmer's point of view, it's simplifying your job, right? Like you don't have to do the rules, but you still have to like figure out the features and whatnot.
Yeah. But there are some trade-offs that come here, because one thing that goes down is interpretability. Like I don't like in this model now, if you tell me that, look, based on this input, I got this output, and you tell me like why, I can't give you the answer. I'll say there are some 13,000 parameters in there. I don't know what they're doing. They gave me this answer.
That's another thing. You have answered one of my questions, because a lot of times I've heard people say like the black box nature of things, and we don't really understand why it's doing.
This is where the black box comes in. Because in the case of the linear regression, it was very easy. If you give me, I know exactly what parameter corresponds to which feature, because the parameter is the coefficient of a feature. And if you give me a new house and my model predicts that your new house has a low value, and you ask me, hey, why does my house have a low value? I can tell you exactly why it has a low value.
Right.
I'll say, hey, my model multiplies your number of rooms by 50.
Right.
Your number of rooms is low. So like your house price is low.
That's a really good example. That's why, like, if we, like, one of the concerns that people have is like increasingly with algorithms making a lot of our decisions, which is happening, right? Like increasingly, it's going to make a decision which might seem unfair to us, and there is nothing we can do about it, and no one will be able to explain why that happened. It's like why we're like one of the examples I can think of is like, imagine you apply for something and if your application is denied. I'm generalizing it, like some application and it's denied.
A credit card application is a good one.
And imagine like your application is denied, but you were not given an explanation why that happens.
Because no one knows the explanation. Like once you get into these, once you increase the like 2 parameters, 10 parameters, yes, it's okay. I can explain to you what's happening. Once you get to 13,000 parameters, it's like no one understands what these parameters are doing.
Right.
And there's some effort going on right now into ML explainability, but it's hard. There's a trade-off between models that are more powerful versus models that are more explainable. And that's just like
I think,
a challenge.
That's okay. I understand. So with every new breakthrough, you're getting more powerful models, but obviously there's a trade-off here, and the trade-off is you're losing a view into what's actually happening.
Because like this thing here is a complete black box. Like no human being can look at this and understand. Like,
it's a scary picture.
Like, you know, mathematically, maybe you can understand some of the equations, but literally you're just saying like there's a bunch of random. Usually this is treated as a vector because you don't say these are 784 individual values. You treat it as one vector with a 784 dimensions or one. And it's all these multiplications that are happening. Usually they're like matrix multiplications because you would treat them all together. So, and that's actually a reason why GPUs are optimized for this task.
Actually, that's what I want to understand as well. Like what NVIDIA, if you have, like, I don't know if you follow stock prices or not, but like if one of the interesting stocks that you could have followed over the last 5-10 years is the NVIDIA stock. It's insane how much it's increased. And I think one of the analogies that people give is like they've observed that whenever a gold rush is happening, the people that tend to make a lot of money are the people who supply gold miners with their equipment.
And picks and shovels.
And in this case, like if you extend this analogy to like AI, like if there's a gold rush happening, then NVIDIA is getting enriched. I understand all that. Like, I don't fully understand. Like, what is it? NVIDIA used to make graphic cards. What happened suddenly?
So graphic cards are actually a type of processor that's optimized for a very narrow function. Whereas it's a GPU versus CPU. CPU is a general purpose computing machine. GPU is optimized for a very specific function, like of rendering graphics, which actually turns out is ultimately matrix algebra. And training of neural networks is all matrix algebra, because at the end of the day, you're doing like millions of matrix multiplications. That's what's going on here. Every time you compute an activation function, every time you have to do that for each and every layer, like, you know, there are 13,000 parameters. So it's just a bunch of matrix multiplications. And a CPU can do that, but it's not optimized for that. So whereas if you take a narrow machine, like a GPU that's just optimized for doing one type of operation, it can scale, do it more cheaply, do it more efficiently.
Okay, that makes sense. Okay.
With the rise of neural networks that made these matrix multiplications like really important, and that's like most of your compute resources are spent doing matrix multiplication, it made sense that we're going to build specialized hardware, GPUs, and then Google built TPUs.
Yeah, tensor processing
yes,
units.
those are also optimized for matrix multiplication. And I think they're actually even further optimized if you use Google's TensorFlow library for doing the
yeah, I want to get into that. Not now, whenever you think it's appropriate, but I want to understand like what is TensorFlow? What? Yeah.
Oh, yeah, we can talk about that. TensorFlow is just a Python library. TensorFlow and PyTorch are the two common libraries that make it easy to do exactly. Like, imagine if you want to write a program that creates a neural network.
Yeah.
Like, you don't want to have to like sit and.
I only bother about this and this. Like, I don't want to be bothered with this. So TensorFlow does all the hidden layers.
And PyTorch, yes.
They do the hidden layers.
They do everything. They create all the... You can define how many layers you want. It's just an abstraction layer on top of this neural network. Like, and it does the training algorithm. Like, you don't have to code how to do gradient descent, how to do backpropagation. They have that built in. So that's ultimately... They're just like high-level Python libraries that make it easy for you to interact with these low-level concepts.
That makes sense.
Yeah.
Okay.
And yeah, Facebook built PyTorch, Google built TensorFlow. They're both pretty popular. I don't know how things will change now with like LLMs and stuff. We have to see what happens. Yeah. But yeah, so that's...
So the big breakthrough first with the classical ML. Sorry if I repeat too much. It's just for my own sake of understanding.
Yeah.
With classical MLs is you don't have to write rules.
Mm-hmm.
With neural nets is you don't even have to give the features or structure the data.
Exactly.
So we're giving, and that way it's becoming more powerful.
It's automated.
And it's also like in some sense like less work even. It sounds like, hey, you don't have to write rules. Hey, you don't have to give features. Just give me the raw pixels and I'll do all that for you.
Yeah.
Obviously, it requires a lot more computational power as can be seen with scary looking math, scary looking graphs.
Yeah.
And you're losing explainability.
Yeah, exactly.
But so I understand. So neural nets can do stuff like this
and deep
prediction.
Learning, if you hear the deep learning term, it just refers to a neural network where you have more than one hidden layer. That's all deep learning means.
Oh, okay.
It means the network is deep.
So deep learning is a type of neural network.
Yes, exactly.
Okay. So if you go back to the circle view, there's AI, there's classical and ML. And then within ML, there's neural nets, and deep learning is type of that, where it's more than one hidden layer.
Yeah, exactly.
Okay.
Yeah.
So now we're down to deep learning, which is like more hidden layers. And now we can do more complex things like image recognition.
Yeah.
This is just a basic example like handwriting.
And we can also do text. Like that. Yeah. So that's the next thing. So we wanted to talk about generative AI, right?
Yeah.